Listen here. Now we are going to derive the expression for path difference. Okay. So before that, before going to derive the expression for path difference, I will explain the diagram which is drawn here. Look at that. It's nothing but it is a double slit. Two slits are there, S1 and S2. In between S1 and S2, the distance is D. Throughout the derivation, we have to use the symbol D. In between the screen and the coherent source, the distance is taken as capital D. Are you clear? On the screen, we are able to observe the interference pattern. These set of bright fringe, dark fringe, bright fringe, dark fringe, this kind of set of bands that could be observed here. Here, the light from S1 and light from S2, both are traveling and finally it reaches the point O. The point O on the screen, that is equidistant from S1 and S2. Are you clear? Since S1 and S2 both are equidistant from O, the waves which are traveling from S1 and S2, both of them, they won't have any phase difference. They will be in phase. Because of in phase, without any phase difference, they are able to create the bright band, central bright band. Make a note. Here central bright band will be created. Understood? So here I have chosen another point P here. We don't know whether the bright band or dark band will be created there. Just to find out whether the bright band will be created or dark band will be created, for that we have to derive the condition. Later we are going to derive the condition for the occurrence of bright band or dark band at point P. This is the sample point which I have chosen on the surface of the screen. From the central bright band, the point P, undefined point P, in between distance that should be taken as Y. Are you clear? In between the screen and the coherent source, the distance is taken as capital D. In between the coherent sources, the distance is taken as small d. Are you clear? Here we are going to learn what is the meaning of path difference. Look at the diagram here. Two sources S1 and S2 are there. Among the two rays, among the two waves which are originating from S1 and S2, which wave travel longer distance? Explicitly it is seen that S2, it is traveling longer distance, finally it reaching the point P. S2 travels shorter distance, is clear, to reach the point P. So that light wave from S2, it travel extra distance of this distance S2m. This extra distance traveled by the light wave from S2 is called as path difference. That should be represented by the letter delta. Are you clear? So here, how to get the delta, extra distance path difference? What we have to do? From S1, we have to draw the perpendicular. After drawing these two lines, S1P and S2P, we have to draw the perpendicular line from S1. There, that perpendicular line, that one gives you the extra distance traveled by the light from S2. So this extra distance S2m is called as, what is this, path difference? That is called as delta. For this delta, to get this delta, we have to derive the expression. Are you clear? So here we are going to derive the expression for path difference. Okay. Now look at the other details of the diagram. Here I have drawn a triangle. Okay, right angle triangle. Here one small angle theta is created. So the same triangle that is drawn here, S1, S2, distance between the two coherent sources D, the extra distance traveled by S2 wave is delta. The same thing is drawn here. And then from the midpoint of these two coherent sources C, I have drawn a straight line. Here you are getting another triangle. There you are getting a bigger triangle. Here one perpendicular is there. By using this triangle, look at the same triangle is drawn here. Same theta, and then distance between C and O is capital D. Distance between P and O is Y. Are you clear? Here, though these two triangles, this triangle and this triangle, both are similar, though their sizes are different, this triangle and this triangle both are similar in all aspects. By using this two triangle alone, we are going to derive the expression for path difference. Okay. Now this distance can be obtained by using these two triangles. So from this first triangle, clear, we are going to derive one expression, that is sin theta. What is sin theta? Here opposite. What is opposite here? Delta. divided by hypotenuse is d. Are you clear? So from the first triangle we are able to get the expression in the form of sin theta. Now let's see the next triangle. There is clear. From this another trigonometrical function tan theta can be obtained. Opposite divided by adjacent. Opposite is y, adjacent is d. Are you clear? Now we have got two equations, sin theta and tan theta. Here the most important thing is here that angle theta is too small. Theta value is too small. How can I say that the theta is too small? Because the distance between two coherent sources is too small. Are you clear? When the distance is too small means definitely the theta, the angle which is created here must be too small. Therefore, the sin value, tan value, both of them they may not have the value. Okay, they will be losing their significance. Therefore, we can remove sin and tan from both the two equations. From the first equation, we can write it as theta is equal to delta divided by d. From the second equation, we are able to get theta is equal to y by d. Now, these two equations can be equated. Delta divided by d and y divided by d can be written. Are you clear? From this expression, we are able to get the expression for path difference. So delta is equal to cross multiply this y d divided by d. So this is the expression for what? This is the expression for path difference. Here this is the extra distance traveled by the second wave. This is the extra distance traveled by the second wave. This extra distance S2m. This is nothing but S2m. That extra distance traveled by the second wave, path difference, that could be calculated. So what is the expression for path difference? Now we can write it as path difference can be represented by, its symbol is known delta, it is represented by yd divided by d. Are you clear? So from this expression we are able to get the expression for y also. What is y? Y is the distance between the central maxima and the point P, where we are going to find out the nature of the fringes. Y is equal to cross multiply this delta d divided by small d. So this is the expression to get the distance. This is the expression to get the path difference. Okay.